So let's talk about the second derivative test for local extrema. So as a quick review, if we just have a function that I've defined here, we can clearly tell where it's got some local maximum and local minimum values here. And we know that we could use the first derivative to help us find that. So we could ask ourselves, where does that first derivative change from positive to negative? So we could see that right there and right there, that those would be two values where our first derivative would change from positive to negative. So on our function, we do in fact have maximums and minimums at those points. But today is about how can we use the second derivative to prove local extrema. In other words, how could I use the graph of the second derivative here to find again or prove that those local and maximum, or excuse me, local minimum and maximums exist. So first of all, this is the second derivatives test for local extrema. What it's going to say is that first of all, the first derivative needs to be equal to 0. In other words, the first requirement is that this needs to be a critical point. So we need to identify a critical point. Just like the first derivative test, we need to identify those because those are the only places where it could possibly exist. A local extrema, so we want to narrow down our, number of choices just to the values where it possibly could be. So the second derivative test will say two things. If we have identified those critical points, what we can do is we can look at the shape of the original function, which again will be defined by our second derivative, to say, well, what does the graph look like there? So if it looks like a certain shape, then we know it would be either a low point or a high point. So the first thing we'd say is that if our second derivative was greater than 0. So in other words, what that's telling us is that our original function, the graph, was concave up. So if we think about drawing a quick function, and I'm just going to use, per se, a parabola, if I do a concave up function, and we've identified this point here, right at point P, that function is the critical value. So what would that be? Would that be a minimum or a maximum? Well, if the graph looks like that, well, then it has to be a local minimum. So if the graph is concave up at your critical point, then there has to be a local minimum there. Now the next thing, or this, I guess the second part to this would say, well, what if the graph isn't concave up? So in other words, what if the second derivative was less than 0, a negative value? So again, we'd say our graph would be concave down. So if I've identified a critical point, P, and I know that the original graph is concave down at that point, well then what it's safe to assume then is that that point, P, must be the maximum because of the shape of the graph. Now, what we will see in a second as well is that there could be a point where the second derivative is equal to 0, or that second derivative maybe isn't defined. So that's another case to consider. Now, if that happens, that won't answer any questions regarding local extrema. That will help us answer some questions in regards to a point of inflection, but we'll come to that in a later demonstration. So first, let's go look at this graphically for a second. So if we have our original function, and now I'm going to graph the second derivative. So if I ask myself, I've already identified, using the first derivative, I've already identified the x value of 1.73, which again, looking at the original function, I'm going to refer to as the square root of 3. What I've already identified using the first derivative test is that I have two critical points where the first derivative is equal to 0. So those critical points then, I would say, what is the value of those critical points on the second derivative? So if I just try to estimate the value at about 1.73, I can see that these values are going to be positive. So the value of the second derivatives is positive. So then again, it's given us permission to know that the graph is concave up. So then that's why we can see that there is a minimum at 1.73. If we look at the negative square root of 3, what we can see is the value of the derivatives down here are all negative values. So the second derivative would tell us that the graph is going to be concave down. So if we have a critical point on a section of a graph that's concave down, it is obviously going to be a maximum. Now, there is a point, this is our clarification, there is a point where that second derivative is exactly equal to 0. And that point where that derivative is exactly equal to 0, we can see is the point 0, 0. Now, that doesn't tell us anything about local extrema of our original function. So if we go look at the original function, the point 0, 0 has nothing to do with local extrema. What we will see in a later video, though, is that point 0, 0 looks like a point of inflection. So we'll connect that point of inflection to the second derivative as well. I think it is important to do one algebraic example of this. The graph helps us see it very conceptually. Let's go ahead and do it with some algebra and some other calculus work. So in this example, we want to use just the second derivative test to find the local extrema of the given function. Again, we could use the first derivative test. That's another valid test to do this. But here we specifically want to look at the second derivative test. So the first part of that second derivative test says we need to identify a critical point, right? So we need to calculate the first derivative. Now the first derivative here, we'll just go ahead and use the power rule and the sum and the difference. So we have our first derivative will be 3x squared minus 18x minus 48. And then to better see where that's going to be equal to 0 or undefined, we're going to factor that out. So we have 3x squared minus 18x minus 16. And a little bit further. So our first derivative, we can see, will equal 0 at the x values of 8 and the x values of negative 2. So again, the reason that we had to do this is we first had to identify our critical points. Now going back into our notes, the second thing that we need to do is to figure out what is the value of the second derivative at our critical points. Are they positive, negative, or equal to 0? So we've identified our critical points. So now we need to find our second derivative. And our second derivative, I'll do in a different color. Our second derivative, again, we'll use that power rule, will be 6x minus 18. And I think it's easier to use this form at that point to see that second derivative. So now what we want to ask ourselves is what is the value of the second derivative at our critical points? So if I plug in 8, our first critical value, I can see that this 48 minus 18 would be 30. So in other words, the second derivative at that critical point was greater than 0. What we'd see over here, if we plugged in our other critical point, negative 2, we would have negative 12 minus 18, which would be, what, negative 30? So we'd see here that the second derivative, in other words, was less than 0. So what that would tell us, if we just kind of conclude, is what we can see is that our graph, at this point here, x equals 8, since the second derivative is positive, this is going to be concave up. Now our second derivative at our second critical point, negative 2, is less than 0. It's a negative value. So what we can see is that this graph then would be concave down. So to conclude our work, that's enough evidence for us to say, so we'll conclude with a nice sentence. So because we have a critical point at 8, so the first derivative was equal to 0, and we pair that with the fact that the second derivative at that critical point was a positive number. There must be, so again, there must be a local minimum at the point 8, and whatever its output would be. And we can go plug that in if we really needed to find it. And then our second conclusion, we also have to, again, in our work state that we've met all the conditions. So because we have a critical point, so in other words, because the first derivative was equal to 0, and the second derivative at that point was less than 0, so the overall shape around that point, x equals -2, was concave down, then we know there is a local maximum at -2, and then whatever its output value would be there. And again, we could just go find that if we really needed to state it. Now, it will be good practice, obviously, just go check that off on a graph. So let's go make a quick graph of our original function. So we're going to turn all these other ones off. So let's make a new expression. So let's go see y equals x, sorry, I remember what it was. X cubed minus 9x squared. X cubed minus 9 minus 48x plus 52. So we'll have to zoom out. We'll want to see, let's look at that maximum right there. So -2, which is again what we said, we thought there would be a maximum at the point -2. And we can see that its output is 104 if we wanted to write that down right now. So -2, 104 is a maximum value. And then we should see also at 8, we'd have a minimum. So let's go find the minimum over here. And we can see at 8, we do see a minimum. Let's get a better viewing window just to see our overall picture. So again, we can see our maximums and our minimums were correct based off of our second derivative test. We could go ahead and label -396.